amine group will come. I'm repeating it time and again so that it goes into your blood. Are you seeing this? I'm repeating it time and again. I'm going into phase, closing the loop, again coming to the examples, again repeating it time and again. You also study in this manner. You also do it in this manner time and again. This is how it will get into your blood. I could have just given you one example and jumped on to the next one, which anyway happens everywhere else. Those who have already gone through in your school and anywhere, they'll just show you one whole process, one example max to max, they will run away. That's all. How you perceive it with you and digest it and actually chew on it and work on it and remember it, nobody is going to tell that. I am doing it time and again to you because this is how you should also be doing when you revise or when you study. Yes, but you have to do it, and that's where RRM notebook comes into picture. If you're not working on your RRM notebook, you're not putting your energy into it. Right now, I am only doing it for you. Yes, so chances are that you will remember it, provided you actually put a little bit of energy from your side. Yes, I have taken you till 90. Last 10% you have to put it. Are you getting my point? Yes, which is required. Otherwise, you can't close the loop. You can't get some marks also. Yes. So, aryl halides, as the name suggests, aryl, this word is coming from what? What is the root word? Root word from which aryl is coming? Anyone? Come on, come on, come on. What is the root word from which aryl is coming? Like alkyl is coming from what? Alkane. Yes or no? Alkynyl is coming from what? Alkene. So, aryl is coming from what? What's the root word?
Arene.
Arene. And what do you mean by arene? Risha, what do you mean by arene? Really? Sangvi, what do you mean by arene?
Aromatic.
Aromatic compounds are also called as arenes. Is that clear? Aromatic compounds are also called as arenes. Organic compounds are classified into three different types: aliphatic compounds, alicyclic compounds, aromatic compounds. Aliphatics, all the open chains. Alicyclic, all the cyclic chains without the aromaticity. And aromatic compounds are the aromatic compounds. Arenes are the aromatic compounds. Good? Fine. And you know their nature. I am not jumping again back to the topic of aromaticity, anti-aromaticity, and non-aromaticity that we have already discussed. Correct? I hope you are cherishing that table which I gave in the past. That one table alone can help you in understanding everything was there. Yes. How for aromaticity you need to have a planar structure and what all should have to be in conjugation for that. Aromaticity keeps on going. Basically, resonance keeps on going. Anyways, coming back here, when it comes to aryl halides, basically chlorines will be attached to what? Chlorines will be attached to the aromatic ring. Like here, this is a chlorobenzene. Correct? Here it is toluene. In that, at ortho position, you have chlorine. So you can call it as orthochlorotoluene also, or 2-chlorotoluene also. That's also fine. Here, what will you call it? Ortho and para dichlorotoluene. Yes, or 2,4 dichlorotoluene. Is that clear? Yes, that is one way. Now, how do we prepare these aryl halides? That's also important. So basically, we have seen these type of reactions. It is nothing but just the reactions of aromatic compounds. Do you understand? It is nothing but just the reactions of aromatic compounds. What do we do with the aromatic compounds? What type of reactions do they undergo? What is the mechanism? Electrophilic, aromatic substitution. Do you remember? Yes? Electrophilic, aromatic substitution. They are aromatic compounds, that's why we call it as aromatic substitutions. Also sometimes called as ESR, electrophilic substitution reactions. Either ways you can call it. Make sense? Some books quote it as EAS, electrophilic aromatic substitution, or they call it as electrophilic substitution reactions. Either ways. Basically, electrophiles are going to attack there on the arenes and they are going to substitute the already present hydrogen. Is that clear? I hope you remember the mechanism. What used to happen? There is a hydrogen at every carbon. Now what will happen? This Cl2, for it to behave as an electrophile, it's very difficult. You need to have somebody else who can release Cl plus. Yes or no? Cl plus can behave as an electrophile, not Cl minus. But what is the nature of Cl? Most of the time, how do you find it in the form of ions? Cl minus. Yes or no? So you need to have somebody much more stronger to bond with that Cl minus, much more in the need of electron to bond with that Cl minus, and that is where AlCl3 plays a role. Are you getting my point? That is where AlCl3 plays a role. Sometimes it is also called as halogen carrier also. Yes, so it carries halogen with it, forming AlCl4 minus. Then Cl plus, which is released, goes close by to this benzene ring. Since there is double bond in conjugation present there, one of the double bond breaks, connects with chlorine. Correct. So one chlorine will come here, and one hydrogen which was already present will come here. But there will be a positive charge now. Yes or no? Correct. And then you cannot show, there will be only two bonds present there. So basically, aromaticity is lost for a moment. Correct. Then slowly and gradually in the next step, this hydrogen will leave, his electron will be utilized to again form a double bond. H plus leaves. That H plus can combine later on when it comes close to this AlCl4 minus. Correct. It will take away one of the chlorine, forming HCl. AlCl3 is once again halogen carrier. AlCl3 is once again reproduced. Got it? Regenerated. And here chlorobenzene remains. Anyways, we have seen that already, that mechanism. So I'm not going into the detail of that. We will see it in our due course in our sheet also. So basically, phenol, how will it react? You know, PCl5 is one of the best reactions which actually can react with anybody who contains OH. That is why, what does it give? It gives test for, again, this is the part of POC. Yes or no? Practical organic chemistry. This gives tests for OH group. Yes or no? Correct. So in phenol also there is OH group. What will it do? It will substitute it. It will form chlorobenzene. Makes sense? And whenever it does so, what gets produced? POCl3, phosphoryl chloride. Nice. And toxic fumes of HCl is given off. Good. All clear? But if you allow more of phenol to remain there, it will start reacting with the phosphoryl chloride, and then rather than producing chlorobenzene, it will produce triphenyl phosphate, TPP. This is such a compound which is used sometimes in antiseptic creams also, TPP, triphenyl phosphates. Yes, correct. Remember this also. If more moles of phenol is allowed to react or remain in that reaction, it will start reacting with the phosphoryl chloride. It will produce TPP, triphenyl phosphate. Good. Another very famous name reaction, which is with the name Sandmeyer's reaction, after the name of a scientist. Here, there is something called as N2. Correct? And this side there will be benzene ring. I'm just showing it with 5. Yes or no? This is called as what? Anybody knows? What do you call this fellow? This is called as azide, azo compounds.
Diazo
Wherever,
compounds.
yes, it is called as, since two of them are coming, it is called as diazo compounds. So wherever these fellows come together, they are highly unstable, and you know, when two nitrogens are together, they tend to release very fast and create and produce nitrogen gas. Yes or no? That is what they do. Nitrogen gas leaves, chlorine goes and connects directly with the arene, forming chlorobenzene. Make sense? Nitrogen gas is given off. Please keep in mind, wherever you will find diazo linkage coming, two nitrogens connected with each other, little bit of heat also, and with the help of some reagents, this nitrogen gas will be given off. Or if not heat, at least some acid. Now here acid is coming in use. CuCl in the presence of HCl, or CuBr in the presence of HBr. What does it do? Causes N2 to leave, and bromobenzene, chlorobenzene, like that formation will happen. The only thing is for iodide, since it is that reactive, that high reactive, that you don't even need hydrogen iodide, any acid along with it. Make sense? Because it is highly reactive. You know its nature. So iodobenzene formation will happen here, correct? And a nitrogen gas will be given off. KCl will join together. All good? Another reaction, again a name reaction, Ball-Schumann's reaction. What happens in Ball-Schumann's reaction? Again, same reaction. Now, who is going to behave here as an electrophile? Now, by the way, here, in all these places, the electrophilic substitution only is happening. Yes or no? N2 is being substituted with what? Iodide ion there. Now, but this iodide ion is not I minus. Yes, it is I plus, the electrophile. Same way here also. You know, BF boron is known for being electron deficient. Yes or no? By nature. Correct? If it is electron deficient, that means it will certainly release somebody who is electron sufficient. Correct? So that is what happens here. Now that it releases F, one of the fluorine, as F plus. Correct? That F plus will go and substitute N2 plus and will join there. Can you see that here? Yes. So basically N2Cl, when they are connected with each other, basically there is a positive charge on nitrogen and Cl minus. There is an ionic relationship here. Correct? Everything else is covalent except these two. Yes. And as soon as this fellow will go there, H plus and Cl minus leaves. Yes. When H plus leaves, BF4 minus will go and join there with N2 plus. They will form this. Heat it slightly, nitrogen gas will quickly jump out. Make sense? And the electron deficient BF3 leaves. One fluorine remains there after electrophilic substitution. All good? Do you remember Hunt-Sticker reaction? We saw it above also, remember? But above there was another name along with this scientist. Whose name? Let me see if you remember. We saw it above. Whose name? Check your RRN notebook. I'm expecting that you are transferring it on a daily basis. Check your RRM notebook. It should be there. Reactions, reagents, and mechanisms notebook. It should be there. Check. That's why I'm telling time and again, what do you have to transfer into that notebook? That one notebook, and you will be the master of organic chemistry. Nowhere marks can be deducted, provided you're working on that notebook at least 15 minutes daily. At least after the classes, you're writing down all the important things, shifting all the important reactions in a systematic manner, as I have told you. What was that? Write down the reactants, basically substrates, initial substrates, then write down the reagent, then write down the any other conditions which are required, any solutions, any pH conditions, any temperature conditions, correct, any acidic basic conditions, write that down. Then write down what product it forms. If you wish to write down one more thing, you can write down there, what does this reagent do? Yes, because in the examinations, they will give you a reactant, they will give you the reagent, they will ask you what product is forming. So in your own words also, you can write down what does this reagent do. Yes, if you write down in one line, okay, if I use Ki, I don't need acid and it will do the electrophilic substitution, iodide ion will get substituted there. This one line will help you because you've written it in your own word. This will stick to you. Are you getting my point? Then in that RRM notebook, you also write down what? Reactions, reagents, and mechanisms notebook. What else do you write down? You write down what is the name of the reaction. Then you write down what is the type of the reaction. Correct? This is Ball-Simmons reaction. What is the type of this reaction? This is a substitution reaction. This is a fluorination reaction in one sense. Fluorine is being substituted. Correct? And what will be the type? Electrophilic substitution is happening here. Correct? That is the way. Anyways, so now we move on to the Hunt-Sticker reaction. Yeah, do you remember the name? What is the name?
Borodin.
Borodine-Hunziker reaction. Here it is only Hunziker reaction. Hunziker alone gave this, not two scientists, but the principle is same. One carbon less will be there in the product. Why? Because that carbon leaves out as CO2 gas, because it is part of a carboxylate ion. Yes or no? Now here silver carboxylate is what is forming here. Yes or no? Now this CO2 is what is going to leave. In place of that, Cl will come. Cl plus will come and join there. Cl minus will combine with Ag plus, forming AgCl. Are we good? All clear? Yes. AgCl. This is ClCl. AgCl gone. Ag plus, Cl minus, Cl plus goes back, substitutes CO2 gas. CO2 gas will come out here. All clear? Correct? Similarly, Raschig process. What are we doing here in Raschig process? Use 2 moles of benzene ring. This time, don't use uh, any other species like some salt of some carboxylate, you know, uh, uh, or any type of azide diazo compounds, and all that is not required. Just use plain and simple benzene ring, but 2 moles of that along with acid, hydrochloric acid, and oxygen gas in the presence of Cl2, CuCl2, copper chloride, which is just present there for the sake of increasing the concentration of Cl chlorine, and also helping, because it is divalent in nature, also helping in taking away what? The hydrogen which is present here. Yes, heat it. What will happen? You will have chlorobenzene, 2 molecules of chlorobenzene forming. Water will be given off. Correct? Now let's quickly jump onto the chemical properties of. This is how we produce chloro, or basically aryl halides. Correct? Or halobenzenes or haloarenes. Whether you call it as haloarenes or aryl halides, they're same. Now let's quickly jump on to what type of reactions will they lead to. How they are produced, how their preparations happen, that we have seen. Now we will jump on to understand what all reactions they lead to, they participate into. So one of the first thing which we learn is that chlorobenzene is essentially inert to aqueous sodium hydroxide at room temperature. This is one thing which you should know. At room temperature, it is not going to react with aqueous sodium hydroxide. Next, any type of aryl halides you pick up, they are usually very less reactive than alkyl halides. And I hope you know the reason. Yes, alkyl halides, they lead to which type of reactions? SN1 most of the time. Yes, SN1, SN2, or sometimes even E2 also. Good, that we know already based on the nature of what type of primary or secondary or tertiary alkyl halide we have, or what type of base is actually attacking in the form of either a nucleophile or a base. Is it bulky or not? Is the temperature high or not? Is the base strong or a weak base? Or if there is one more condition was there, what type of solvents are you using? Are you using polar protic or polar aprotic solvents? All that we studied, yes, in the last class. But here most important part is aryl halides do not participate in reactions as vehemently as alkyl halides do. They're less reactive. Why? Think about it. Why?
Sir, in aryl halides, like usually in aromatic compounds, resonance take place, which increases the stability, so less reactive.
That's a bit crude way of saying. Yes, because of resonance, they have a special characteristics. Rather than nucleophilic substitution happening of this chlorine, they activate the different zones on the aromatic ring where electrophilic substitution will happen. Yes or no? Rather than nucleophile coming and substituting this fellow. Are you getting my point? Yes or no? If it was CH3Cl, it can participate with aqueous KO or alcoholic KOH. You know that, correct? And KOCH3 CH3OH and all that formation will happen. But if you do the same thing here, will this OH go and this nucleophile will go and replace Cl? No, because it doesn't have electron. The very next moment it is given to the ring. Yes or no? And once it is given to the ring, some of the zones in the ring are activated, either ortho or meta or para. Correct? Since this is a moderately activating group, correct? What will it do? Or actually weakly activating group, what will it do? It will activate which zones? Ortho and para positions, where the electrophiles will attack. That means there is more electron density at where? Ortho and para positions, where electrophiles will attack. No question of nucleophiles coming into picture. And that too also is very tough because it is always in delocalized position. Yes or no? Correct. So that's why they are very less reactive. Good. Next, carbon halogen bonds of aryl halides too strong. Yes, they are too strong. In fact, the very next moment they become double bonded. Cl becomes Cl plus. You remember when it gives away his bond to form a double bond? Yes. That means it doesn't have the strength of only a single sigma bond. It will have a strength in between single bond and double bond. Yes or no? Correct? Correct. Next. Aryl halides, carbon halogen bonds of the aryl halides are too strong. Aryl cations are too high in energy to permit aryl halides to ionize readily, as it happens in an SN1 type of process. Yes or no? Correct? A carbocation formation happens, na? Yes or no? In a nucleophilic SN1 SN2 reaction, carbocation formation happens. And then later on, what happens? Once a cation is formed, who will attack? Who will attack? Nucleophile will attack.
Nucleophile.
Yes or no? Correct? So if it is SN1, in the second step, nucleophile attacks. If it is SN2, right in the first step itself, nucleophile attacks, causes the carbocation formation. Yes or no? So point is, carbocation, as soon as it forms, it is so much stabilized by what? Resonance, that it is not going to participate so easily. Yes? Yes? It is not going to ionize so easily. Next, the optimal transition state geometry required for SN2 process cannot be achieved. Do you remember transition states which form in SN2? Yes? 5-membered ring. That cannot happen here because already there is a bulky structure. Yes? 5-membered ring cannot form here. Next thing is nucleophilic attack from the side opposite the carbon halogen bond is blocked by the aromatic ring. You remember always in the SN2 there used to be a back attack of the nucleophile. Yes or no? Causing which type of inversion? Which type of inversion?
Walden inversion.
Walden inversion. Yes or no? Correct? From D to L in enantiomer changes, or L to D in enantiomeric inversion used to happen. But that cannot happen because here at the back you have this bulky fellow, Humpty Dumpty. Yes or no? The benzene ring is present here in the form of Humpty Dumpty. It doesn't allow the nucleophile to come from the back and attack on that bond. Yeah, that's one. So these are the reasons which are going to prominently play role when it comes to the chemical reactions of aryl halides or haloarenes. Are we good? Yes. But they do participate in some type of reaction, and there is a special reaction which they lead to, which is called as elimination addition mechanism of the nucleophilic aromatic substitution. They do lead to formation of nucleophilic substitution. What is this, sir? You were saying it doesn't happen. It may happen, but you will have to use a very, very strong base. Correct? You will have to use a very strong base, such as sodamides or potassium amides. Remember? We have seen them. Yes? NaNH2 or KNH2. So these are, when used, they may lead to formation of nucleophilic aromatic substitution, but then also there is a transition state species which is produced, which actually leads to the formation of this. That fellow is known as, you've seen about them, you've seen him, benzene. Do you remember? Where we studied about electrophiles, nucleophiles, and we studied about carbenes and nitrines and benzynes. In GOC, we have already done it. Yes or no? We have seen these benzynes already and what type of reactions they lead to. One such reaction is called as elimination followed by addition, which is called as elimination addition mechanism. Yes, of aromatic compounds. Let's see that. So when you use that, so then what will happen? Even those without electron withdrawing substituents, they will give some products. And what type of products? Chlorobenzene. Now, in this, the carbon which is present here is not the normal C12 carbon, it is carbon 14. Yes, just to check where does that electron moves, that carbon is used as carbon 14. Yes, at number 1 carbon. Correct? As soon as the strong base reacts there, it will substitute, an amine will come there. You have formation of aniline, but with carbon 14. Understood? That extra electron, that dot is showing, basically there is a carbon 14. Correct? But it can also lead to formation of either at this bond, because double bond, na? Correct? Either it can lead to the formation of amine at this place or at this place. So this aniline first, or aniline 2 aniline, 2C14 aniline, or 1C14 alanine, both are possible. Let's see the mechanism, how exactly it happens. So very first step I said elimination, then later on addition. Yes, first elimination of this chloride ion leading to the formation of benzyne. Let's see that. So what will happen? Amide ion will come closer. What will it do? It will snatch away H plus. So the electron of the bond of electrons of H hydrogen will be utilized to form a triple bond here. Now you know this is very unstable. That's why benzynes are reactive in nature. All the unstable fellows, whether it is electrophiles, nucleophiles, free radicals, carbenes, benzynes, isn't it? Nitrines, all these are unstable fellows, and that's why they are reactive. And among all of them, free radical is the most. You know that already, correct? So this is how benzyne formation happened. Are we good? Why is it unstable? Because in this planar structure, what is the hybridization of this carbon and this carbon? Think about it. sp hybridized. sp hybridized, the angle is 180 degree. But in reality, what is the angle here? If it has to remain in a structure of 6 fellow connected in a cyclic way, this bond angle should be 120 degree. Yes, it is 120 degree in reality, but it was supposed to be 180 degree, a difference of 60 degrees. That high angle strain will be there here. Yes, angle strain you can call it, or van der Waals strain you can call it. Yeah, so that's why it is unstable in nature. Anyways, so benzyne formation happened. That is important for us. Once you have benzyne ready, ammonia gas is off, Cl minus has left, then starts the addition phase after the elimination. What happens in the addition phase? In the beginning of the addition phase, once again this amide ion comes there, anion. Now this time it will give his electron, because he is behaving now this time as a nucleophile. See here carefully. He is behaving as a nucleophile. A strong base is now behaving as a nucleophile, giving his electron to that one of the electron deficient carbon, which is forming triple bond, and joining there. Once it joins, now it has double bond, the other carbon will have a negative charge. Good. This is called as aryl anion. Yes, whichever benzene derivative is present there, it will have a anion formation. So aryl anion formation happened. Then in the next phase, the addition will happen. What happens in the next phase? Now this time that ammonia which has gone away, will come close to it. Then this electron will be given to that hydrogen, H plus. His electron will be utilized by the NH2, forming NH2 minus, and that is where hydrogen will attach there, forming aniline. Is this clear? We are back with aniline. Where did we start? Let's close the loop once again. Where did we start? We started with chlorobenzene. In the first step, elimination had to happen and benzyne formation was required. Yes, so elimination happened, H plus elimination happened, and benzyne formation happened. In the next step, addition phase has started, in which again this amide ion comes back and attacks as a nucleophile. Even though it is a base, attacks as a nucleophile, joins there, leading to the formation of anion. aryl anion. And then in the next step, that aryl anion will give its excess lone pair to snatch away H plus from the ammonia, forming amide anion, and you will have aniline formation. Nice and easy. This is the mechanism which will follow everywhere wherever nucleophilic substitution is going to happen of the uh, haloarenes. Okay, I think this part I already told you. The sp2 orbital in the plane of the ring in benzene is not properly aligned for good overlap. Thus, pi bonding is weaker than alkynes. Good? Correct? That's why it is more reactive. Okay, same type of reactions with orthochlorotoluene. Make sense? Same type of reaction. First benzene formation. I hope you're able to understand. And once again, another amine group will come. I'm repeating it time and again so that it goes into your blood. Are you seeing this? I'm repeating it time and again. I'm going into phase, closing the loop, again coming to the examples, again repeating it time and again. You also study in this manner. You also do it in this manner time and again. This is how it will get into your blood. It's my I could have just given you one example and jumped down to the next one, which anyway happens everywhere else. Those who have already gone through in your school or anywhere, they will just show you one whole process, one example max to max, they will run away. That's all. How you perceive it with you and digest it and actually chew on it and work on it and remember it, nobody is going to tell that. I am doing it time and again to you because this is how you should also be doing when you revise or when you study. Yes, but you have to do it, and that's where RRM notebook comes into picture. If you're not working on your RRM notebook, you're not putting your energy into it. Right now, I am only doing it for you. Yes. So chances are that you will remember it, provided you actually put a little bit of energy from your side. Yes, I have taken you till 90. Last 10% you have to put it. Are you getting my point? Yes. Which is required. Otherwise, you can't close the loop. You can't get some marks also. Yes. Okay. So benzene formation happened in the first stage. Elimination happened. Now addition will happen. NH2 will come and join there. Make sense? Addition happened. Correct. Now it can join at both the places, either at this end or at this end. Both are possible. So ortho methyl aniline can also form, or meta methyl aniline can also form. Nice or not? Now the question arises, sir, when it was orthochlorotoluene, here we made chlorine at the ortho position. But when it came to this fellow, we are considering this fellow as our main active group, and according to him, he is at ortho position. So orthomethyl toluene, orthomethyl aniline, we are saying. Why is that? Priority. Again, once again. I hope you understand. Yes? Based on the priority of the activating and deactivating group, we are doing this. Is that clear? Good. Okay. And that table I have already given to you. I hope you will go through it. Again, this time you have parachlorotoluene. This here it was orthochlorotoluene. Now you have parachlorotoluene. So you have a benzene formation between meta and para. You will have a triple bond. Then addition will happen. Now this time NH2 can go to meta position also. Correct? Meta to this methyl, or basically methyl goes to meta or at para. So these two formations are possible. Good? Good. This is how we have to see. Only positions we have to see. That's all. Once you, this is the power of mechanism. Once you've understood, now you know now that okay, NH2 can join at this carbon also, at this carbon also, wherever benzene's benzene's triple bond is forming. Yes or no? Correct. Now, if this fellow is there with you, you know what will happen. 3-methyl benzene first formation will happen. The ortho para can lead to, or 4-methyl benzene and meta and para. Why is it ortho written? It is meta. Do the correction. Meta and para formation can happen as we saw above. Good. Now, nucleophilic aromatic substitution by the addition elimination mechanism. The generally accepted mechanism for the nucleophilic aromatic substitution in nitro substituted allyl halide. Now, this time we are doing nitro substituted. This time, what are we taking as substituents? We are not taking NaNH2. What are we taking? Since we are going to substitute it with some okay, so this time we are taking it sodium NaOCH3. Can you see that? Now, who is the base here? Who's going to behave as a nucleophile? The oxygen of the OCH3 minus. Yes or no? Na plus will leave with Cl minus, will form NaCl. That is fine. But what this OCH3 will do? He is the one this time who will attack and join, forming what? Attack on the benzene and will join there. Correct? Yes or no? Does it make sense? That is what happens here. Is this clear? Who is the solution here? Methanol at 85 degrees Celsius. Good? Okay. Another one. This also, by the way, happens via same mechanism. I hope it is clear. Yes? Addition elimination mechanism only. Correct? Now, an orthopara group exerts a comparable rate enhancing effect. Metachloronitrobenzene, while much more reactive than chlorobenzene itself, is thousand of times less reactive than either ortho or para-chloronitrobenzene. Is this clear? Correct? They've clearly told here that ortho and nitrophelo, they exert a comparable rate enhancing effect because they are more reactive, and meta one is comparatively less reacting. Yes, almost 1,000 times. Yeah? Okay. Effect of ortho and para nitro substitutions. Let's see. This is your chlorobenzene. As soon as you bring a nitro group there, now what is happening? This fellow is an activating group, and this fellow is a deactivating group. Yes or no? If he is deactivating, he is sucking the electron. So he is giving his electron via minus M effect. Sorry, minus M sorry, plus M effect. Correct, and he's pulling the electrons, decreasing the electron density over the benzene ring, arene ring, via minus M effect. Yes or no? I hope you remember. Correct. Now, via all that process, basically chlorine is the one who is becoming most electron deficient site. Yes or no? Chlorine is the one who is becoming most electron deficient site. Now, who can easily attack here? Who can easily attack here? Talk to me. Who can easily attack here?
Nucleophile.
Nucleophile can easily attack, and that's why nucleophilic substitution happens. Yes or no? Addition followed by elimination. Are we good? Fine. Bring one more NO2, put it on ortho position also. Oh my god, all the more. Two of them are pulling. Bring one more, make it trinitro chloro chloro trinitrobenzene. Then it's all the more. In fact, very, very violent reaction. So fast that you can't even measure it. Can you see that? These two itself are going at the rate of 10 to the power 10 and 10 to the power 25. What to talk of trinitro? That's why TNT, you've heard about it? Is used in making bombs. Trinitrotoluene. Yes? Okay. Highly violent reaction. Okay. So in contrast to nucleophilic substitution in the alkyl halides, where alkyl fluorides are present, see here now what is happening. Already this makes the bond quite unstable. Sometimes you don't even need some stronger fellows. But here what happens, when it was alkyl halides, you didn't need any of these bases and all that. This bond itself was very unstable and breaks, and automatically reaction happens in case of that. But here, since its electron will be utilized in increasing the electron density of the ring, it is a mildly it is a activating group. Yes, going to increase the electron density over the benzene ring. That's why aryl fluorides, they can undergo nucleophilic substitution, and they will need some strong bases which can behave as a nucleophile. That's where this KOCH3 or NaOCH3 comes into picture, which will substitute fluorine and will join there. All good? Yes? Okay. Now, ortho or para-nitro. Okay, next. Indeed, order of leaving group, reactivity in nucleophilic aromatic substitution is the opposite of that seen in the aliphatic aliphatic substitution. That is fine. I mean, if you put fluorine there, it is most reactive. Correct? Usually, what we used to see, if we used to talk about alkyl halides, we would say Ri is most reactive, then RBr, then RCl. Yes or no? And then RF. Make sense? Remember? But here it is opposite. Who is most reactive? Chlorine. 312 times more than chlorine. Correct? And then bromine is slightly lesser, iodide is slightly more less. All these are actually found, reactivities are found towards sodium methoxide. We have kept that constant in methanol, and temperature also is kept constant. Then it is measured, the reactivity. Yeah. Okay, kinetic studies are done on this, and it was found that it is a second order nucleophilic substitution reaction, bimolecular nucleophilic substitution reaction, SN2. That means it will depend on the concentration of the aryl halide also, it will depend on the concentration of the nucleophile also. That's why they also play a major role even in case of fluorines also. It is a second order kinetics. Yes or no? Bimolecular second order kinetics. So it will have a rate determining step in which there will be two molecules involved, and it will have a second order kinetics. That means rate will depend on both the concentrations of the species. Okay, mechanics, let's quickly see this. We've already kind of seen this, but anyways, once again addition stage. This fellow will go close by, he will also get attached there, double bond is broken, as you can see here. This has led to the formation of an intermediate, we can call it as some anion intermediate or cyclo hexa dienyl anion, we can call it. Yes. And then in the next step, what will happen? The neighboring hydrogens electron, the lone pair which is there on the neighboring hydrogen, where the bond had broken. Yes, double bond had broken. From there, it will jump. It will form a double bond there. Once the double bond formation happens, somebody has to leave. F minus leaves. Good. And you have nitro, para, nitro, and benzene ring with OCH3 has a common name. I hope you remember that. That is called as anisole. Yes. So para-nitroanisole formation happens. Is this clear? Mechanism is clear? Yes. Mechanism is clear. In the first step, addition and then elimination. Addition followed by elimination. Exactly same thing will happen in these further reactions. Dow's process follows the same thing. This time we use aqueous NaOH, high pressure and temperature. You will have phenol formation with NaCl. Again, how? Benzyne mechanism, same addition elimination mechanism. Good. Then presence of the deactivating group. If you put any deactivating group at the ortho position or at the para position, that will make the nucleophilic substitution even more easier. If chlorobenzene itself is reacting, maybe if you put a nitro group here or a nitro group here or a nitro group here, that becomes all the more reactive. That we have already discussed. Yes or no? Correct. Provided you put a deactivating group. If you put an activating group, what will happen to the reactivity? It will decrease. Yes or no? Yes, one of the year that had come as a question in I think NEET, or some years back even in JEE mains also. They put a activating group, and then they asked you to prepare, which one is most reactive among the following, or which one is least reactive among the following. Yeah. Okay. Many times people got confused because they've only studied about, okay, comparison is between chlorobenzene and maybe some deactivating group nitro and all that, and there'll be one place, one OH sitting somewhere, or some other fellow sitting there, an activating group in place of a deactivating group. That becomes least reactive in this nucleophilic substitution reaction via benzyne mechanism. Good. Good. Addition elimination of benzyne mechanism. Okay, so reactivity order goes this way, that we already discussed it. Nice. Fine. Any doubt so far? Okay, so same way, bromobenzene, use a strong base. In the presence of liquid nitrogen, low temperature, you will have aniline formation. Use it with copper cyanide, you will have, and pyridine as a solvent, 300 degrees Celsius, high temperature, you will have a cyanobenzene. Yes or no? Plus copper chloride. Fittig reaction, very famous Fittig reaction. Take two molecules of chlorobenzene. What will happen? Two molecules of NaCl will leave. They will connect with each other. Do this in the presence of diether and little bit of heat. You will have diphenyl formation. Interesting reaction, isn't it? But same mechanism again, everywhere. Wunsch-Fittig reaction. This also you have seen already. Yes, NaCl will leave, and this propyl group will go and join with the benzene, propyl benzene. Nice, correct. Then formation of aryl magnesium halide. What is it? What is it? Who is this fellow? Grignard reagent. Isn't it? It is a Grignard reagent. In the presence of tetrahydrofuran as a solvent, this reaction is carried out with a divalent magnesium compound. Magnesium will jump in the middle and will form a Grignard reagent here, aryl magnesium halide. The mechanism of all this you know already. Exact same way as aliphatic uh, Grignard reagents form, even aromatic Grignard reagents form via same method only. Correct? That mechanism doesn't change. Normal reduction. Normal reduction use nickel surface, nickel and aluminium surface in the presence of a base NaOH. You can get from halobenzene back our benzene. They get substituted. They are basically reduced. Correct? With chloral, this is very important. Listen to this: CCl3CHO, trichloroethanol. Trichloroethanol is a very important compound. Imagine you have a carbon connected to three chlorines, and that is connected to C double bond OH. Now, this chlorine is already highly electron deficient. Yes or no? Yes or no? Because of this oxygen present here. Make sense? Now imagine if three more chlorines come on the very alpha carbon via inductive effect, minus I effect. All three of them will pull the electron density over this carbon even more, making it much more electropositive. Yes or no? Prone to the attack of a nucleophile. Yes? Makes sense? Correct? So that is what happens. What will attack? The benzynes will attack there. Those are our nucleophiles. Yes or no? Benzynes will attack there and they will join in place of C double bond O. First one of them will attack, then one other will attack. The double bond O is actually gone. Make sense? Or one easy way to catch it is one easy way to do this reaction is, let me remove all this and show it to you at least. Okay, let's only this box go. An easy way to see this is uh, this two hydrogen and one oxygen gone. Nice. Dehydration. In the presence of sulfuric acid and heat, dehydrating agent and heat, water leaves, rest of it connects, forming what is very important reaction, especially from your board exams point of view, DDT. Actually, you will have to study about an experiment also on this. How do you form it? Maybe if laboratory it is there in function is functional in your school, then they will even teach you to do this experiment in lab. Yes, with the help of chloral reacting with 2 moles of chlorobenzene, you can actually form dichloro diphenyl trichloroethane, which is an insecticide, DDT. Yes, correct. At the para position, two chlorines are connected. Okay, now electrophilic substitution. Back to our ESR, electrophilic substitution reactions. I hope it is clear. Use FeCl3, one more chlorine, either at ortho or para position. Why? Because chlorine himself is activating group. So ortho para activating groups are there. Okay, next HNO3 nitration is happening. A stronger acid than HNO3 is used, which is H2SO4, causing not just H plus to leave, rather NO2 plus to leave, and that NO2 plus substitutes Cl minus. Sorry, not substitute Cl, substitutes H plus either on the ortho or para position and forms uh, orthochloronitrobenzene or parachloronitrobenzene. Same way, sulfonation. So this was nitration, then sulfonation, exactly same way. I hope you remember Friedel-Crafts reactions of two types: Friedel-Crafts alkylation, Friedel-Crafts acylation. Correct? I hope you remember. We have seen these type of reactions. All these are examples of electrophilic aromatic substitution. And with this, we are done with what is called as alkyl halides and aryl halides. There are some solved examples, interesting solved examples I want you to go through. Just few of them. Yeah, good. That's all about this chapter. Next time when we meet, what are we going to do? Alcohols, phenols, and ethers. Please come fast.